Jawo Jackson Nick, Wohin Gausing Li Dao Zerli. Yeah? Okay. Unfortunately, my Duolingo subscription doesn't go much further. So I have to do this in English. I apologize. All right. So today I want to talk to you about modern service networking. I want to talk to you about a new feature of Consul called Connect. And I want to talk to you about how you can use it with Kubernetes and how we can use Envoy. Super easy. So I work as a developer advocate at HashiCorp. And I've worked in the industry for like over 20 years now. I have quite a lot of gray hair. And the key thing that I've always struggled with, I've always had a problem with when I've been building systems is that networks are a pain, right? And network security is a pain. And then you add dynamism, like schedulers, like auto-scaling groups, and the pain is just amplified. But now we've got the service mesh. So before we talk about Connect, let's look at what is our problem, right? What is the problem with networks? So the problem with networks is that when you don't treat them right, when you think about things in terms of this, the perimeter firewall, because you think, well, hey, I've got a perimeter firewall and therefore my application's safe. But that's not true, right? Because the key thing is about the way that a lot of modern attacks are working is that people are bypassing that perimeter firewall. And they're bypassing it because they're looking at application code level vulnerabilities that gives them an access into your network. So I really like this quote from the Symantec security report, and it states that, you know, one of the key phases in most targeted attacks is what's known as lateral movement. Attackers rarely look out and manage to compromise the computer. And this is kind of the key thing, right? That once you've compromised that perimeter firewall, this is when an attacker can run amok in your network. This is when they're going to be starting to look around and try to do the real damage. They're not necessarily going to be stealing all of your data from the first service they hit. Right. Simple example. How does that work? Well, as an attacker, I've identified that you've got a service, and it's a front-end service for your e-commerce website. It's a favorite service. It doesn't have any real data. But what I've identified is that there's a vulnerability in this application. It's Node.js. There's a framework vulnerability which allows me to do remote code execution. From that remote code execution, I can execute operating system commands on the underlying container because, well, the container's not that secure either. But the key thing is that that's not my destination. Like, I can't really get anything out of that service. But what I'm starting to do is I'm going to start to look to move laterally. I want to be starting to probe the network, looking for other services, looking for other opportunities that I can move deeper into your system, potentially other systems that have vulnerabilities that I can attack. So what I do in this instance is I manage to get in deep enough. I manage to start being able to read traffic off your network. I realize that you've got an order processing system. I realize you've got a transaction processing system. But actually, you know, they're secured. You've got JWT. You've got authorization between those two services, except you're not using transport level encryption. So I've got into your network, I've snooped around, I've identified two services which I should have no permission to be able to interact with, and I've retrieved your admin token and the payload, and that's all I need to be able to execute a further attack inside your system. You know, that in itself is a sort of, it's like an e-commerce example, right? But the key thing is around a lot of the recent sort of exposure, it's not so much about financial loss, it's about data. So we really do have to be thinking deeper than that perimeter firewall when we're sort of looking at network security. So the two problems. So the two problems that we had in this previous attack, which is not so uncommon, right? Open network access. I had absolute freedom of movement right the way through your network once I'd bypassed that perimeter firewall. Mistake number two. You assume that because that perimeter firewall exists, that you don't need TLS internally. You know, you terminate TLS between the client and the gateway, the endpoint, but internally, hey, the firewall's good. I don't need TLS. You do need TLS. So let's address those. So open network access. So you know, this kind of traditional approach around just having a perimeter firewall, this kind of what's often commonly known as a castle and moat approach, this is not a new problem. This is a problem which was solved a long, long time ago. It was solved with the problems around realizing that you need network isolation. That the second that you can't protect your infrastructure with physical security, with four walls, that you need to be thinking about how do you separate the responsibilities, how do you separate the traffic inside to avoid these lateral movements. And network segmentation is the solution to that. You know, again, this is like a 30-year-old solution. This was a solution that was invented probably shortly after the network itself. But what network segmentation does is it kind of states, let's break up the network. Let's break it up into areas of risk or areas of trust. So let's, for example, break it up into front-end services and back-end services. Now, moving deeper than that, we're now working in a multi-tenanted environment. So, you know, you've got multiple applications running on a single node. You've got multiple containers running on a single Kubernetes node. And we need to kind of go deeper than just network level segmentation, and we need to start thinking about service level segmentation. Because potentially those areas of risk, those areas of trust are now mixed into the same node. So with service level segmentation, we're kind of applying the same approach, where we're sort of stating that we want this ability to control traffic between services, but it's predominantly on kind of like a node level or on an application level. And all those things are great, except we have high availability. So a big cheer for high availability and a big boo for what it does in terms of networking, because it adds the complexity. Because with a static environment where you're controlling IP addresses, you can manage routes, you can manage network security far easier. But in a dynamic environment, you don't know what the IP address of an application is until after it's appeared. And potentially you still don't know. And dynamic environments are not just your Kubernetes clusters, but they're your autoscale groups, potentially vSphere. You know, it's quite a broad spectrum, which makes it a really broad problem. So how do we deal with this? So we've got two problems. One is that the application deployment is disconnected from the network configuration. What do I mean? So I mean that, you know, the applications are not being orchestrated by you directly. They're being orchestrated by a machine. But then how do you manage that in terms of controlling firewall routing? How do you control things like, you know, sort of routing tables and stuff like that? It's not an easy problem, because what we want to do is we want to be able to do this. We want to be able to state that service A can only talk to service B. So in the kind of this old network segmentation mode, I'm going to configure my routing rules to only allow those two service A instances, .12 and .10, to talk to my service B instance, .1. Potentially also add some firewall ports. In the dynamic environment, that changes all the time. It changes without me knowing it. So how do you kind of keep on top of that? These are kind of the challenges which we face with modern network security. Add another layer of complexity. Kubernetes, our schedulers. We don't even know potentially which node an application is running on. The application is going to be spread across a number of nodes. And that makes configuring those routing rules even more difficult. The more application instances you've got, the more difficult those routing rules are. So what you end up doing, and I don't blame anybody, is you end up sort of segmenting your networks, but allowing entire subnets for your cluster. And as we kind of saw, that can be a big risk. What we want to be able to do is have a dynamic model for network segregation. We don't want to be defining things on static network locations. We want to be basing things on application ID. So we want to take an intention based. I have the intention that application A talks to application B. It's simpler and it's dynamic because as the applications are rescheduled, you don't need to keep reconfiguring those rules. So our second problem, TLS. What about our TLS? So kind of one of the key things in this sort of an attack is with that lateral movement, the ability to read data off the wire is really, really dangerous, right? I mean, there's two things as an attacker. When I get inside your system, I can go straight for your database. I can try and sort of attack the database inside the store. But if you're not using encryption on your transport, I don't even need to. I can just read the data straight off the wire. Does that take longer? Yes, takes longer. Is that a problem? Well, maybe not. Because OWASP stated that it can take up to 180 days before you detect a breach. So that means that somebody could be in your system, snooping around, reading your data for 180 days before you notice it. And if you look at sort of a recent attack on a British airline, there was something like 40 days before they noticed. And this was like a public script, right? You know, there was a public script on their website that they didn't realize that was harvesting data for 40 days. So imagine that when it's hidden deep inside your system. I think 100, you know. So why don't we use TLS internally? Well, so if anybody's ever tried to implement TLS internally, service to service, not using internal load balancers, it's difficult. You've got to manage things like certificate authority. You've got to do things like distributing keys and certificates to be able to terminate TLS. You've potentially got to be able to change your code on your application to be able to reconfigure the endpoints for TLS as opposed to just plain. And all of these things are kind of challenging, but they don't need to be. Because I'm not the bringer of doom. What I want to talk about is the easy option, and that's the service mesh. You know, there's been a lot discussed about service meshes. I mean, I think KubeCon last year over in the US was the first time when there was a huge number of talks. There's a lot of interest, and there's a lot of interest because they solve really difficult problems in a very elegant way. So they work predominantly because you end up with these two layers. You have your control plane, which is your centralized and distributed, highly available control plane, and you have the data plane. So your control plane, this is like your Istio, Consul Connect, data plane, again, sort of Envoy, probably the most popular data plane at the moment. It's the one that most of the service meshes seem to be adopting. And these two components work together to be able to provide the functionality that we need to gain this security. So the control plane, this is giving you the features such as service-to-service communication policy, that ability to control intention-based routing as opposed to IP-based. Observability, so the kind of a handy way and an easy way to collect all of those metrics and to be able to have a central point of fanning them out into whatever collection source that you're using. It gives you something which is really important, and that's a service catalog. Because in order to do a sort of a dynamic-based routing, you've got to have a service catalog. You've got to have the ability to understand which services exist and where they are. You don't, as a user, need to know where they are, but the control plane needs that information. And kind of importantly, it needs the ability to manage a certificate authority. It needs the ability to be able to generate the X509 certificates which are needed to secure the TLS endpoints. Also, we need a way of configuring that data plane. If we had to configure the proxies, the data plane every time for every single application instance, that would be somewhat challenging. So the control plane, again, makes that easy for us. So the data plane, and this is going to be generally localized to your application, but these are things that you're looking at in terms of authorization, right? So you're not just dealing with TLS, but you're dealing with mutual TLS. So that's TLS, which is encrypting the traffic, but also identification by using client-side keys and certificates. Request tracing, an easy way of getting those sort of HTTP or whatever sort of traffic metrics between your services. You know, I still think you need to augment your services with certain observability metrics, but the service mesh gives you a lot of stuff out of the box. Hystrix fat client stuff. Like, I've stood and I've talked about the need for building reliable applications, the need that you've got to embed into your code things like circuit breaking, timeouts, you know, configuration around load balancing, retry logic. But that takes effort, that's hard, that requires language dependencies. Even Netflix themselves said that Hystrix as a library was one of the something they didn't like. It was a dependency which every microservice had, and which was something which in some ways broke that microservice pattern. But this data plane can handle all of that for you. It allows your application to be somewhat network agnostic, to be dumb. And that's a good thing because you've got then a centralized capability for that information. So how do you deploy it? So do I need to reconfigure my application? Is there going to be a huge amount of recoding that I need to do? And the answer is no, because we leverage patterns like sidecars. So we leverage a pattern where we're injecting the data plane, injecting the Envoy proxy into an isolated environment like a pod with our application. So in our pod, our application binds localhost. It is absolutely not accessible from any other service externally. It can only be accessed from Envoy. Now, Envoy is exposing the sort of the ingress into the application. So all traffic's going to flow through Envoy and then into your application. And by that, you don't need to change any application code in order to do things like service-to-service authentication or implementing TLS, because Envoy is terminating all of that for you. It's managing it for you. So where does Consul come into this? So Consul was brought out onto the market 4 or 5 years ago, and it was primarily HashiCorp's approach at solving the problem which systems were dealing with at the time, which was service discovery, distributed configuration, and health checking. So it's been hugely successful. There are like millions and millions of downloads, and there are some absolutely massive clusters of in excess of 20,000 nodes of Consul. A lot of people will rely on it on a day-to-day basis for not just running modern applications and schedulers like Nomad and Kubernetes, but also for running sort of more legacy applications, for doing service discovery in like VM fleets or actually even on physical machines. And the architecture of it looks like this, in that it is a highly available system. So you have a cluster of server nodes. So you're going to run a quorum. You're going to have 3 or 5 or 7, and these are going to be running inside of Kubernetes. And the way this works is that Consul has the concept of leader and a follower. So the leader is the thing that manages the consistency. It's the thing that ensures that you've got reliable replication of data across all of the cluster. And the followers can kind of serve requests, but only if they're reads. Any request which is a write, for example, an update to a service catalog, for updating health checks or anything like that, changing any of your Consul Connect intentions, they get forwarded to the server, and the server is only going to write those to the RAF log when it's received a quorum of responses from the followers. So it makes it very highly available but highly consistent. When you're interacting with Consul, you don't talk directly to the server. And the reason that you don't do that is because we want to make this thing performant. It has to be highly distributed. So a lot of the capabilities in terms of things like caching of service catalogs, the ability to do all of the health checks, they're done by the clients. So you don't need to load balance a Consul server because all you do is talk to the client. The client is 100% aware of the state of the cluster, where the leaders are, where the followers are. If there are any unhealthy cluster server nodes, it's got built-in capabilities around retries. So that makes it, again, operationally simple and very, very reliable. When you're building that out into Kubernetes, you end up with something like this. So you end up with your quorum of Consul servers. They're going to be running on your Kubernetes nodes somewhere. It doesn't matter. You know, that's the beauty of the modern scheduler. But on each of the nodes, inside of something like a daemon set, you're going to be running each Consul client. So your pods which are running on the node will talk to the local Consul client. The Consul client then delegates that request to one of the server nodes. In terms of health checking, I kind of briefly touched on this, but the way that health checking works in Consul is it's distributed. It makes it highly performant because the local nodes are performing the health checks on the local servers. There's kind of a second layer of health checking, which is that the actual clients, Consul clients, are sending a heartbeat back to the server, and if the server doesn't receive a heartbeat, then it'll declare that the entire node is out of operation. This is using the SWIM protocol, which a lot of distributed systems are going to use, and I'm kind of proud to say that HashiCorp research have published a paper on some enhancements to the SWIM protocol to make it more reliable, which of course is implemented in Consul, but is also open sourced so that other people can implement it if they're using SWIM as well. So our CA, we still have our certificate authority. And I mentioned inside of the control plane, one of its responsibilities is managing that certificate authority. So in Consul Connect, you have the built-in certificate authority. Now, that's going to serve all of the purposes around generating, allowing you to rotate your root certificates, leaf certificates, signing requests. But in addition to using the built-in CA, you've also got the capability to leverage HashiCorp Vault. So if you're already using Vault and you're using Vault for your PKI infrastructure, or maybe you need the capability to use an HSM for enhanced security, then there's an optional and pluggable Vault integration as well into Connect. So kind of just a quick overview of how it works is that the client's going to generate the key pair. It sends that request to the Connect server for signing, and potentially, if you're using Vault, it'll forward it on. But then that's going to sign your certificate. We use the SPIFFE standard. Really pleased that SPIFFE's made it into the CNCF. I think it's a wonderful initiative to kind of try and standardize identity. But one of the things that you want, again, around certificates is rotation, and that's important. Stale TLS certificates, long-lived certificates, you want to try and keep TTLs on things as short as possible. One of the nice features of Connect is that it allows you to do root level rotation on your certificates. And the way that works is, in the traditional flow where you have a root and intermediary and the leaf which would be given out to the service, when you want to rotate a root, what you can actually do is issue another root, create a new root and load that into Connect. What Connect will do is it generates new intermediaries and cross signs with both the old root and the new root, and then reissues the leaf certificates. So whenever your system's in operation, when it's validating those certificates, it doesn't matter at this point whether it's got the old root or the new root, because both of those are active. Eventually, once we can kind of transition away from the old root, then we move over to the new. So we've got this capability of having this uninterrupted, seamless ability to rotate root certificates because of using this cross-signing, because the intermediary is going to be valid against both. So intentions, like what's simpler than that? You know, the capability to just say, I want to allow this communication between two services by using the service name. I want the ability to deny the communication between these two services. And we'll see this a little bit more in depth when I do a little demo, hopefully. Envoy, like, it's the obvious choice. It's fast becoming the industry favorite method of the data plane for your service mesh. And rightly so, it's a great piece of software. So kind of just quickly how this all ties together then is that the way that it works is that when Envoy starts, it's going to get bootstrapped. And then when it sort of starts up, it's going to connect to the Consul client. It's going to obtain its certificates and the keys that it needs to be able to secure the endpoint with mutual TLS. So it does that because what we've done is we've implemented the XDS, the Envoy XDS API, inside of Consul. The next step is that the Consul client is then going to get those certificates signed. It's going to delegate that to the control plane. And once that key bundle has been passed back, then Envoy can start to secure those connections. We've got to think about updates. We've already mentioned that we want to be able to rotate certificates, that we want seamless updates to our system. And we're going to do that in a very sort of low overhead way, because the client is issuing a blocking query on Consul, which means that it's kind of saying, when you get some updates on X, let me know. And that's a really low overhead. It's not polling, it just maintains that. And Envoy's doing the same thing because we've got that persistent gRPC connection between the client and Envoy. So that's a bidirectional streaming API, which means that the Consul client can actually push information down into Envoy. In terms of when you get that connection, so the client's going to initialize a connection. They're going to do a little bit of the TLS handshake. Envoy is going to request that the client sends its client certificate as part of the MTLS flow. So that client certificate has got that X509 spiffy identity encoded into it inside the URI SAN. And only if the certificate is signed by the right root, then will that connection be allowed. But there's an additional step because we want to validate. It's not just a case of, is this connection presenting the valid identity, but it's, is this service allowed in my intention graph? So Envoy is going to make a call again using that XDS API to Consul, and it's going to say, I've got a request from service A, is this okay? Is this allowed in the intention graph? And Consul will give a yes or a no. So that whole process is not terribly inefficient, because actually what's happening is between those two Envoy proxies, you can end up with persistent connections. You know, you want to be able to maintain the persistent connections. You want to avoid having to do the MTLS handshake every time, every request. And you certainly don't want to be doing the re-authentication every time, because that's going to cause a centralized dependency on the control plane, but also it's going to slow down the application. So it's a very, very, very low overhead. So in terms of how we segment, well, this was our previous problem, and we said that the reality was going to be this. But that's fine, because What we're now doing is we're segmenting by using intention-based security. All of the exposed ports in the system are MTLS secured. You've got to have a valid identity in order to be able to connect, whether it's open or not. I'm going to show you in a second how you deploy it, but really, really easy. Consul Helm chart, run it up on top of your Kubernetes cluster. And I think the important thing is that Sidecar injection, so really simple setup using pod annotations. It would be wonderful if everything was Kubernetes, but it isn't, unfortunately. We have to deal with legacy systems, and Consul Connect allows you to deal with that too. You can integrate Consul Connect as easily as you're running it on Kubernetes as you can with like a Java-based application on a Linux VM, or even a Windows-based application running on a, well, Windows virtual machine. And even physical infrastructure too, right? There is still some of that. L4, of course, you can then use it for your databases. And if you want to go to the next level, you don't even need to use the sort of the configured data plane. If you need super low latency, then actually you can use the software development kit. So this is an example of how you can make a direct gRPC connection using the software development kit. And this relies on no sort of proxy at all. So let's take a look, hopefully. So my Trafic is on a 4G MiFi device, which is proxied out to the US, to the UK, and my server is out in the US. So I don't know what could possibly go wrong with that. Okay, finally. All right. So let's take, go away. All right, let me make that bigger for you. So the first thing that we need to do is to just install Consul on our Kubernetes cluster. So I've got a pretty bare Kubernetes cluster here. So let me just run the Consul Helm chart. So I'm going to do Helm install -name, I'm going to call it Consul. And I've just got the Helm chart locally. And that's going to install. So the benefit of using Helm is it's going to give you a capability of running Consul if you're not already running it, using tooling that you're already familiar with. You can safely and securely run Consul on top of Kubernetes. I mean, it's just an application. Maybe my Wi-Fi's died. Okay, did I mention that there was an extreme danger that using a proxied connection across 2 continents might cause a problem with a demo? Right, okay. So let me show you what I was going to deploy anyway. So this is like predominantly all I'm going to need. I've got a very standard pod definition here. So I have a service that I'm going to create, because this is a sort of a forward-facing service inside my cluster. I'm going to specify some ports and things. A deployment, really nothing weird going on there, right? Number of replicas, and then my template. Now the The difference is that if I want to enable Consul Connect on my cluster and to add that Envoy data plane into my pod, I don't have to write anything special. I don't need to define any special containers or set up any special configuration. I'm just going to use the annotations because Consul Connect has Kubernetes integration into it that allows you to just specify the annotation Consul Connect equals true, and then I can specify my upstreams. Because in the same way that I'm only talking localhost inbound via my Envoy proxy, when I want to make a call out to a service, then I'm going to talk localhost as well. That's the way that Envoy works. It means that I don't need to worry about the whole kind of hystrixing, the circuit breaking, the load balancing, because Envoy is performing that functionality for me. So I tell Envoy, I want you to connect to this service, and it'll expose me a localhost port, which makes my application configuration super easy. Moving down there, again, there's really nothing special going on, nothing complicated. Oh, it did come up. But unfortunately, I'm out of time. And I do apologize about that. But let me just quickly summary. All right, so demo bad. Simple architecture, easy to run Consul Connect. Use the Kubernetes Helm chart. Look at our problems, right? TLS is hard. You've got to do the CA thing. You've got to work out how to distribute certificates. You've got to work out how to rotate keys. No, you don't. You use the service mesh because that's its job. It does all of that for you. When it comes to things like configuring that network segmentation to be able to reduce the blast radius in the event of a breach, you don't need to worry about the dynamism which is given to you by your scheduler, because the service mesh allows you to not worry about physical network locations, about IP addresses, and to just concern yourself with service identity, and to leverage that MTLS to not only give you encrypted traffic, but authorized connections. Please go and try it out. Look, the Helm chart is super easy to use. Check out Consul and some more of the documentation at consul.io. Helm chart can be found in our GitHub repo at github.com HashiCorp/Consul Helm, and we are moving to get this as part of the official Helm distribution. I think there's a PR open on that. If you do have any questions, I will be outside and I'm more happy to chat, and maybe I'll even finish my demo. But thank you so much for listening. Some contact details there if you do want to contact me, but thank you again.